This is an exercise on solving trig equations using identities. So we put everything pretty much together. We take the identities that we've been working with the last little while, the proofs and the substitutions, and we couple that with the equations that we were solving a few weeks ago. So it really isn't a big stretch, but it does make for a messy looking question. Now, a certain type of equation may require an identity in order to solve it. And basically it works like this. If you have an equation that has more than one type of trig ratio, that is if you have a sine and a cosine together, well, because you've got two unknowns, you can't really solve for it. But with the use of identities, you can occasionally simplify them. So let's begin. Find all values of theta in the domain 0, between 0 and 2 pi. So we are in rads. Question doesn't state it, but I'm going to work out exact value measurements for it. So you cannot just push this through your calculator and get an answer for it, because your calculator will give you decimal answers for rads. And here we start off with cos theta is equal to root 3 sine theta. So this is equivalent really to something like x is equal to root 3y. You can't work that one out unless you are able to get it in terms of a single trig ratio, either cos or sine or other. So what we do, a little bit of algebra on it, we divide both sides by sine theta, which I'll do promptly. And that's going to put this into a form that we can work with. Now I am, in the course of this division step, I am also noting, although I'm not going to write it, that we cannot have values for theta that would be equal to 0 or sine theta. So we do have to consider restrictions, but that won't be a big issue for us here. And then after that, we'll note as well that cotangent theta is equal to cos over sine. So we then have it in a form that we can work with. So let's do that. And the reason I divided by sine instead of by cos is because I want it to be with the number on one side, the trig ratio on the other. So now we get cosine theta over sine theta is equal to square root 3. And be aware, these questions we are solving for something. They're not proofs. They're not just a simplification. We want an answer. And then that's going to break down or be replaced with cotangent theta. And we've been here many times before. We cannot solve this question in terms of cotangent. We need to put it in terms of tan. And tan theta, if cotangent is equal to root 3 over 1, tan is equal to 1 over square root 3. And there is that 3-point system for these. We become aware of the quadrants. We identify the quadrants that we're working with. And tan is positive in quadrant 1, because they're all positive there. It's also positive in quadrant 3. And then our reference angle. If this is in degrees, you could just push it through and go second function tan, and you'll get the answer. And some people do it like that, and then they convert it over to rads. I'm not going to, though. I'm going to recognize, based on those special triangles, that tan theta equal to 1 over root 3 is going to give us a reference angle of pi over 6, or 30 degrees, if you were thinking like that. And once you get there, that means we're going to be in these two quadrants. And pi over 6 there, pi over 6 there. This is an optional step. You don't need to draw it. However, you do have to write your answer in its rotational angle form. And that diagram can help. But we will for sure get theta is equal to pi over 6 in quadrant 1, and then 7 pi over 6 in quadrant 3. So that's the way they work. And this particular one is a fairly common type of setup where you just have cos and sine, and the only trig identity that will simplify them will be tan or cotangent. The next one will require a little bit more from us. So here we have cotangent theta is equal to, plus cosecant theta is equal to cosecant squared theta plus 1. So we actually have two different trig functions, and to make it worse, one of them has two parts, a quadratic, the cosecant squared, and just the linear variable. That's not good. But when you take a look at your formula sheet, you will see that there is a trig identity that links cotangent squared and cosecant squared. And that's the one we want to go with. So we have a choice. We could either convert the cosecant squared into cotangent squared, or we could convert the cotangent squared into cosecant squared. And I would recommend the latter. I would suggest that we go cotangent into cosecant, simply because we have another cosecant there, and it would make more sense to get everything in terms of cosecant and then see where it takes us. So with a little manipulation of that expression, we go cotangent squared equal to cosecant squared theta minus 1. We now have our substitution. So I have a new screen up for that, and I just make the substitution. Cosecant squared theta minus 1 plus cosecant theta is equal to cosecant squared theta plus 1. So it's all in terms of one variable, which is good. Now you might recall when we were dealing with trig equations before, we would take a problem like this and we would use a substitution, say pick a letter like A, just so it's easier to work with. I'm not going to, and I'm not going to because I look at this one, and when I do clean it up, when I bring everything over to one side, I will note that my cosecant squareds will cancel. So we're actually just left with cosecant theta, and then when you add that 1 onto both sides, it's equal to 2. So all that turned into a very, very simple question. And even though it's in a reciprocal form, we can deal with that by expressing it as sine. So sine theta is then equal to 1 over 2. And this is positive. And sine is positive in quadrants 1, where they're all positive, and quadrant 2, where only sine is positive. And as before, I go after, try to find a reference angle. And sine is equal to, the sine ratio is equal to 1/2 when 4 angles of pi over 6, or 30 degrees. So then you then take, in quadrant 1 and quadrant 2, you take that pi over 6 there, you take that pi over 6 there, and then work out your answer, which would be pi over 6 in quadrant 1, and then pi over 6 in quadrant 2 would be 5 pi over 6. And so there are our two answers. And we got lucky on this one because it canceled out so nicely. We didn't have to deal with quadratics. Let's take a look at one more. 2 sine squared theta is equal to 1 plus cos theta. So we have a squared term and a non-squared term. Doesn't leave us with a lot of choice. We cannot use sine or tan or cotangent because they would have both the sine and the cos would have to be to the same exponent. So really, we have to use this one, where sine squared theta is equal to 1 minus cos squared theta. Now, I didn't write out the original, cos squared plus sine squared is equal to 1, but we've seen this enough times, I think you're hopefully comfortable with it. And we cannot change cos into sine because cos is not squared. So this is our only choice. So we take that sine squared, and we replace it with that 1 minus cos squared. So we would get 2 bracket 1 minus cos squared. You need that bracket around it. If you don't, you probably won't distribute the 2 in the way you should. And what I'm going to do next is what I had been doing earlier with these equations, is I will make a substitution. And I'm doing that just to make my life a little bit easier. So let A be equal to cos theta. I'm just doing this for the sake of the algebra. So this becomes 2 times 1 minus A squared equal to 1 plus A. And this is 2 minus 2A squared is equal to 1 plus A. We have a quadratic equation, which means we need to take it all over to one side and set it to 0. I'll take it to the right side. I'll take that 2A squared over, so it's positive. The A is already there, positive. Subtract the 2 away and we get minus 1. I'm not going to spend a lot of time on the factoring of it, but it does factor. Factors into 2A and 1 and 1. So I usually do these things, I stack them vertically, but I'm not going to in this case because it's a fairly routine one. So we'll get 2A squared. If you FOILed that out, you'd see that it works out. I'm also going to cut a few corners when I set them to 0, and I'm just going to state that A is equal to 1/2. And the other A value is equal to -1. So we're going to get two sets of answers that emerge from this. But we are in the red zone now. If A is equal to 1/2, it means that cosine of theta is equal to 1/2. And we do the usual thing. We identify the quadrants, and cosine is positive in quadrant 1, like they all are, and also in quadrant 4. And if you think, look at your unit circle, or look at your triangles, or just memorize, or use your calculator in degrees. If you keyed that in, you would get 60 degrees or pi over 3 as your reference angle. So if you were to rough that in, I didn't draw this to scale, didn't see the need. And this will give us then an answer in quadrant 1 of pi over 3. And carefully, if you go into quadrant 4, look at your unit circle or work it out by longhand, that would be 5 pi over 3. So those are our first two solutions, but we're not done. We have to work out that A equal -1. Now this is also a quadrantal, and with quadrantals I advise you to either check the unit circle out or use your calculator, or just do it the regular way, because you can do that like that. Cos theta is equal to -1 will solve by identifying where it's negative and getting your reference angle, but not really necessary. Where is cos theta equal to -1? The answer is 180 degrees or pi. So if you did the whole thing together, there are your three solutions. So in this case, we got 3. So that's all you need to do. So those are 3 examples of these types of problems, very good exam problems. They involve identities, they involve the trig equations, plus, of course, the algebra in between. So they're very valuable in that sense. Thank you for your